In Chapter 4, we start talking about proof techniques, and in particular, we're going to talk about the direct proof. Right, so the goal here is we want to prove some stuff, but in order to be able to prove things, we first need things to prove. So we're going to introduce the idea of theorems, so statements that we can prove, that we know are true, and we need to sort of have some built-in, well-understood words that we can base our theorems on. So as we're doing our proofs, we have to be able to know what we're talking about, so we have to have good definitions for words. So that's what we're going to talk about here. We'll introduce the idea of a theorem in section 4.1, and then we'll talk about definitions and some particular definitions of terms that we're going to need to build up our proofs in section 4.2. So starting off with theorems, a theorem is just a statement that is true and has been proved to be true. So obviously I can't prove it to be true unless it is true, so maybe we don't need to say both of these things, right? But for us, theorems are going to be true statements, and we know they're true because we can prove them. We've actually seen a bunch of statements before in calculus, so we've copied some calculus examples here from the book. So the first one says, let f be differentiable on an open interval I, and let c be a point in I. If f of c is a maximum or minimum value of f on I, then f prime of c equals 0. If the sum from k equals 1 to infinity of ak converges, then the limit as k goes to infinity of ak equals 0. Suppose f is continuous on an interval ab, then f is integrable on ab, and every absolutely convergent series converges. All right, so these are some different theorems that you've seen in Calc 1 and Calc 2 about sequences and series, and also about continuous functions, both derivatives and integrability. But there's some things that we can notice here, right? We see a lot of these terms that we've talked about previously. So we're seeing a lot of if-thens, right? If, then, suppose this part, so that's sort of like the if, then this is true, and then this one is going to be a for every, right? For every x, for every absolutely convergent series, we know that series converges. So these are the things that we want to sort of pick up on now that we're used to these languages. All right, so yeah, again, what are we noticing? We're seeing a lot of conditional statements. A lot of the statements we're going to see are going to be these conditional statements, and conditional statements are the type of statements you can prove using direct proof, which is the technique we want to talk about here. So there's lots of different ways I can write it. I can specifically write if-then. We can have a suppose, right? This one's a little bit different because it can be written, it's right now written using a quantifier, but I could also say if a series is absolutely convergent, then it is convergent. So I can write that as an if-then as a conditional statement too. So these are the type of statements that we're going to focus on right now. These are the type of theorems we're going to focus on, is the ones of this if-then form. All right, so the big thing, right, we talked about theorems. There's a couple terms related to theorems that we should become comfortable with. So the theorem, right, these are usually reserved, this term theorem is reserved for sort of big, important facts that we're going to prove. So we're going to call a lot of things theorems, but you might see that when you have some sort of less important statement that you're proving, that might be called a proposition instead. So a proposition, I don't know why that's hard to say. A proposition is just a statement that's just like a theorem, but maybe not as important to a theorem. Now, sometimes when we're trying to prove theorems, we need a little mini step to help us along. Those mini steps are called lemmas. So this is sort of a mini proof. Well, it's a statement, and then we have to prove that statement that helps prove a bigger theorem. So we'll see these in action. And sometimes after I've proved a theorem, then that theorem is going to have some result that's really easy to show right after it. And that result is called a corollary. So a corollary is a result that follows from a theorem. Now, as I'm looking at this, I'm noticing that I spelled corollary wrong, so why don't we go ahead and fix that? There's only one R in it. Don't want to mislead you. There we go. Whoops, now I've got two O's. Let's just rewrite the whole thing. C-O-R-O-L-L-A-R-Y, corollary. So it's going to come after a theorem. All right, so let's move on and talk a little bit about 4.2 here. So in order to prove things, right, I have to have sort of somewhere where we're starting. We have to kind of have some terms to start out where we all agree what those means. So we're not going to start and do things super formally. We're not going to start from a set of axioms, but we are going to have some sort of basic definitions that we can pull from. So there's going to be 9 terms here we want to define. Some of them we'll talk about the definitions of in this video. Other ones we'll talk about later. But those terms are even, odd. We're going to talk about what it means to have the same parity and the opposite parity. So those will actually be the ones that you're going to define. We'll talk about what it means when one number divides another number, and then what a divisor or a multiple is. And then we'll talk about prime numbers and GCDs and LCMs, so greatest common divisors and least common multiples. So before we move on, I encourage you to take a second, see if you can come up with definitions for each of these terms. Our first discussion question here is to actually go ahead and define these 4 concepts. So I want you to see if you can write down a definition for what it means for an integer to be even, what it means for an integer to be odd, and then what it means for 2 integers to have the same parity or to have opposite parity. So go ahead, see if you can come up with those definitions, and we'll talk about those in class. Okay, so we've got a definition here. It's actually of 3 different terms. So we've got divides, divisor, and multiple. So what we want to think about is how we can actually understand a definition. So maybe you haven't seen this word divides used in this context before. So we're going to practice sort of unpacking a definition like this. So I say, okay, I have A and B, and they're integers. So let me just write that down. A is an integer, and B is an integer. And I'm going to say that A divides B. So I write that A divides B. We'll see this symbol in some of the homework questions. So to get that in tech, it's \mid, M-I-D. So I'll just pop that in there for you. So A divides B if B is equal to A times C for some C in Z. So there exists some C in Z such that B is equal to A times C. All right, so that's kind of hard to picture exactly what that means. So what I would like to do here is I like to pick numbers that would make this true. So maybe I'll let A be like 7 and C be 3. And then B could be 21 because it has to equal 7 times 3. So now I know that I can say that A, which was my 7, divides 21. So 7 divides 21 since 21 equals 7 times something, where that thing is an integer. So now I think it's going to help make sense of what this means, right? A divides B means, right, if you do B divided by A, you get an integer. So another way to say this is that B divided by A is integer. So A divides B if B over A is an integer. So I could say 4 divides 16 because it goes evenly into 16. 5 divides 15. 7 divides 35. 2 divides any even number, and so forth. But I would say 3 does not divide 16, since 16 is not evenly divisible by 3. So this is my does not divide symbol. And again, if you want to try to tech that, you can do backslash, n mid for that not mid. All right, so now let's go for the rest of these words, right? We've probably seen divisor and multiple before. So let's pick an example here. So I've got 7 divides 35. Since 35 is 7 times something, where that thing is in Z, just practicing using my definition. So then, again, this is my A and this is my B. So A is a divisor of B, right? 7 is a divisor of 35, and 35 is a multiple of 7. I think the multiple is the one we're probably most familiar with. So now that we've defined what a multiple and what a divisor are, I want you to see if you can come up with the definitions for the least common multiple and the greatest common divisor. All right, so I have 2 integers, a and b, and I want you to define the LCM, the least common multiple of a and b, and the GCD of a and b. Okay, we have one more fact here that we'll use a lot in proofs, and it is that the integers are closed under addition, subtraction, and multiplication. So now, if I'm going to give you this fact, right, I have to tell you what it means to be closed under these. So I say that a set is closed under some operation. So I'll just define closed under addition. If for all A and B, let's call that set S, in S, the sum of those, because I'm thinking about addition, is also in S. So what it means is that the integers are closed under addition. If I think about addition, that tells me that if A and B are integers, so is A plus B. The fact that they're closed under subtraction means that if A and B are integers, then let's use set notation here, A minus B is an integer, and for multiplication, if A and B are integers, then so is A times B. Right, so again, this is a fact that we're going to use in our proofs. So for our final discussion question in this video, I want you to think about this idea of sets being closed under different operations, and I want you to decide which of the common number sets that we've talked about is closed under addition, which ones are closed under subtraction, which ones are closed under multiplication, and which ones are closed under division. So you can think about the integers, the natural numbers, the real numbers, the rational numbers. You can think about things like R plus, the positive real numbers, whatever you want. So think about taking these sets, analyzing them, changing them a little bit if you need to, and decide which ones are closed under addition, which ones are under subtraction, multiplication, and division.